Hello everyone. How are you, Anish? Anish, you are there? Yeah, good evening, Nandana, Shravya. Anshuman?
Yes,
Anshuman,
ma'am.
123, you are there?
Yes, ma'am.
Anshuman, are you attending all the lectures?
Yes, ma'am.
Okay, good. Okay, you guys are ready with your PhD design data book? Okay, good, good. Quickly open your PhD data book. We'll go through the V-belt section and then we'll come back to this design. As per my book, it is 7.58, page number 7 chapter. What is the first table for V-belt design wherever it starts in your book? Mine is 7.58. What is that first table indicating or showing? Sushmita? Sushmita, you are there? Standard sections. So you are getting cross section for the symbol A, B, C, D, E. Then you are getting usual load on the drive. Then recommended minimum pulley diameter, nominal top width, nominal thickness, and the weight per meter of the belt, right? What is the next table indicating? Omkar. What is the next table indicating? Nominal inside length and the pitch. From the formula for length of the belt, the length that we are getting is the pitch length, the nominal pitch length. And the belt is designated using the inside length. Now, when we will calculate the length of the belt, that will not be a standard length, right? You will get different values for different diameters. But as I said, a V belt is selected, it is not designed. So you have to select from the available standard V belts. So if you select either a lower one or a higher one, close to whatever you have designed, there would be a small correction factor which is given in the same table. Correction factor FC is given. We'll see how to use this. Turn the page. What is given after this table? Tanvi. What is the next section in the V belt? PhD data book. Tanvi. Riddhima. Designation is given, which is saying that it is designated by its cross section and its inside length. This we have seen. Then we normally assume the ratio of diameters, which are inversely proportional to ratio of their RPMs. You can multiply with efficiency, assuming 98% efficiency. Then based on the speed ratio, center distance is given. Minimum center distance is sum of their radius. It's little more than sum of their radius. It is 0.55 times d plus its thickness. And the maximum is twice the sum of their diameters. So we'll be normally picking up the center distance equal to d plus d, which will lie between C minimum and C maximum. Formula for length of the belt is now given. Turn the page. What is the next table? Turn the page. What next? Divakar. Transmitting capacity. So this is giving you from the first table for a given belt cross section how the value of power, rated power in kilowatt hour, that is calculated. So these formulas are given for a reference. We are not going to use these formulas, but this is only for you to understand how, using experiments in the laboratory, how the power rating for a given cross section is calculated. Below that, you would get a speed ratio range d by d and the small diameter correction factor. I'll tell you how to use this table. Similarly, for the equivalent pitch diameter and belt speed, how to get the power rating in kilowatt. This also I'm going to discuss. Turn the pages. Come to correction factor for arc of contact. You'll have 5 pages for A, B, C, D, E sections, and the next table is correction factor for arc of contact. Which is giving you angle of arc of contact on a smaller pulley and the correction factor for VV belt and V flat belt. We are using VV belt where on both the sides of the V belt there is a taper. A V flat belt will be having a triangular surface on one side and a flat surface on the other side. So it is a special kind of belt. But we are normally by default going with VV belt. And the last page will be giving you the correction factor depending upon light duty, medium duty, heavy duty and extra heavy duty. And we'll be using this correction factor as well. There's one more page which is giving you the number of belt, formula for number of belt and the dimensions for the standard V grooved pulleys. So I'll tell you how to read this design data book, and before we actually start solving the problem, let us quickly see what are these correction factors and how to find out the number of belts. Should we start? Visual? Okay. Both the Prajwals have agreed. Well, this is the formula for the rated power in case of V-belt drive where K is what? What is K? Ujjwal? Ujjwal Kumar,
Yes,
K?
T1 by T2.
It is T1 by T2. And then we have these three tensions. This is the belt tension, responsible for the load carrying capacity. This is the centrifugal tension and this is the bending tension. And this is the peripheral velocity. Using this formula, the value of PR is calculated and it is listed in the first table in the V-belt drive in the design data book. Now, how those values are calculated? So those values are calculated for the lab condition, assuming theta is 180 degrees, which means both the pulleys are of same diameter, velocity ratio is 1. There is a specific length of the belt which is selected, and this length is given in the data book. So if our length is different from this specific length, we have to multiply some correction factor, and it is assumed that there is no shock. So in case of shock, in case the service conditions change, we multiply it with the service factor. So how our problems would be different? The practical conditions would be different, and so we have to use different correction factors. So we'll see what are these correction factors first, and then we'll see while solving a problem, how do we incorporate these correction factors. So correction factors are used because the real life conditions are different from the lab conditions. They are not same. So these correction factors are required. So the first correction factor is angle of contact factor K theta. Listen carefully this section of correction factor. So we got the formula, or we got the values of rated power, assuming the angle of contact is 180 degrees. So if the value of theta is 180 degrees, this factor K theta will be 1. But the input pulley or the driver pulley is always a smaller pulley with the angle of contact less than 180 degrees. And the moment this angle of contact is less than 180 degrees, we'll see in the design data book the value of K theta is also less than 1. And as the value of theta goes down, e raised to mu theta will go down. What will happen to T1 by T2? This factor, this will increase or decrease when theta goes down. This will also decrease, and when K value decreases, the value of rated power also decreases. So actual power will be the rated power given in the table multiplied by K theta, where K theta is less than 1. So the actual power transmitted would be less than the rated power given in the table. This is angle of contact factor. Since the real life condition says the angle theta is less than 180 degree, so the value of K theta is also less than 1. Is that clear? Next type of correction factor is equivalent smaller diameter pulley factor. Equivalent smaller diameter pulley. This factor will normally use the term DE. Assumption is in the lab condition theta is 180 degrees, which means diameter D1 is equal to diameter D2. This is a rare situation when both the diameters are same. This, as I said, is a lab condition. Both the diameters are same and the angle is 180 degrees. So in actual condition, what happens is one of the pulleys is smaller, another pulley is larger. Value of theta, the smaller pulley is less than 180, the larger pulley it is more than 180. So the smaller pulley diameter is reduced and the larger pulley diameter is increased. So what happens to the bending is, here if there is a bending stress sigma b, because of the smaller pulley it has to bend more. In the smaller pulley this bending becomes more severe as compared to this pulley, and the larger diameter pulley is having a diameter more than this D2. So if here this is D and D, this is my D1, this is D2, my D1 is less than D and the bending stress becomes more severe. My D2 is greater than D and here the bending stress is less severe. This value of bending stress reduces. And there is, it is not balanced. And so what do we do is there is a virtual value of dE. It's an equivalent pulley diameter. So it is assumed that in an equivalent system, the value of D1 is increased to dE and the value of D2 is reduced and brought it equal to dE. D1 is increased to dE and D2 is decreased to dE. So dE is a value lying in between D1 and D2. So this value of a factor with which we are multiplying, this is again given in the formula, in the design data book. Depending upon what is D by D, it is given in the design data book, or it is D2 by D1. So depending upon what is this ratio, we get this factor. If we multiply this factor to diameter and we use an equivalent smaller pulley diameter, and for this equivalent smaller pulley diameter, we'll see what is the rated power. So this rated power is again lesser than the power which is given in the first table in the design data. So this part is little tricky. So this we'll discuss again. Keep in mind, this is used only to calculate or select the value of actual power from the design data book. This value is not used for calculating the peripheral velocity. You are not going to use this for calculating the peripheral velocity. This is only used to pick or select the value of actual power transmitted with this correction factor. So I repeat, equivalent smaller diameter pulley factor is a factor which accounts for the variation in the diameter of the two pulleys. So we are assuming a virtual value of a diameter which increases the smaller pulley diameter and which reduces the larger pulley diameter. Okay? Things would be more clear when we start solving the problem. Next is length of the belt correction factor. Length of the belt correction factor. We call this as, say, KL. So in the lab condition, a specific length of the belt is taken, which is given in the specific length table in the design data book. But actually, when the length changes, length of the belt changes, the center distance also changes. So the center distance is either little more than this center distance, or it is little less than the center distance. In both the cases, we have to take a factor, whether you are selecting a lesser value given in the table or a greater value given in the table. What would happen with the change in the center distance to the bending stress? If your center distance comes out to be greater than the center distance given in the lab condition, what would happen to the bending stress? Bending stress would increase because it has to bend more frequently. No. If the center distance is greater, one of the pulleys here, let me exaggerate it, another pulley is here. So belt is straight from here to here, and when it has to bend, it has to undergo bending when it is traveling through the pulley. Again, it is straight and then it has to bend. So for same RPM, if the center distance is larger than the lab center distance, the bending stress will become less because it has to bend less number of times. And the moment this bending stress is less, when this is less severe, I have to say this is less than the normal lab condition, the factor KL, this would be greater than 1. And if the C is less than the center distance assumed in the lab condition, then the bending is more severe than the normal lab condition, due to which the factor goes down, and if the factor goes down, your rated power also goes down. We'll be multiplying the actual power with the rated power into the scale. So depending upon what is at center distance we are selecting, accordingly this factor is multiplied and the actual rated power would increase or decrease. So this is the length of the belt correction factor. And the fourth one is the working condition. A working condition or the service condition, this is again given in the design data book. This takes into account all kinds of shocks and the working condition, how severe, how mild or extra heavy duty is considered. So ultimately your final power transmission capacity actual, this would be the rated power that you are selecting from the table, from the very first table. This is multiplied with your angle of contact correction factor. This is multiplied by your length of correction service factor. This PR value you have taken for equivalent diameter table, and if the shock factor or the service factor in some of the design data books, this would be given as greater than 1. In other design data book, this would be given less than 1. If it is greater than 1, this value of Ks should be multiplied or divided. Use common sense. Different design data books are giving different values for service condition. If the value of service condition is greater than 1, will the actual power transmission capacity reduce or increase? If Ks is greater than 1, we divide it with Ks. So actual power transmission capacity reduces. And if it is less than 1, then we multiply. And if it is greater than 1, we divide. So without wasting a minute, let us start solving a problem. A V-bell drive is used to transmit. Take the problem statement, we'll solve the problem and then you can ask me queries if you have. Because I'm sure it's not clear to you as of now. A V-bell drive is used to transmit 15 kilowatt power from a 1440 RPM motor to a reciprocating compressor at 400 RPM. Assume the compressor is working for 12 hours per day. Suggest suitable belt. Suggest suitable V-belt. So we have to give the length of the belt, we have to give the cross section of the belt, and we have to give the number of belts that is required. Okay, open your design data book and give me for 15 kilowatt power, which cross section is most appropriate. Give me the cross section. B and C. For B cross section, the maximum load it can withstand is 15. For C, 15 is lying in between. This is page number 7.58, PSG design data book. PSG design data book. Now we have two options, either all of us solve it only for B or only for C, or half the class, roll number 1 to say 60, will solve for B cross section, and 61 and onwards will solve for C. What do you say? Is it okay we solve two problems, or should we go with only one cross section? Vaishnavi? Manas? Two problems. Okay, good. So 15 kilowatt is lying in the range for B as well as C. If we assume B cross section, where roll number 1 to 60, they will be giving me a solution for B cross section, and 61 onwards, they are giving me for C cross section. And then we'll compare which one is better. Right? Better as in the cross section, the size of the pulley, the width, the number of belt required, everything. So those who are selecting B cross section, give me what is the minimum pulley diameter. $125. This is minimum. We'll normally take a little higher than this. So you can take 130 or 140. 125 is not wrong, but this is the minimum. So it's a good practice to take a value little higher than this. For C section, C is 200. We'll go with say 220. Because this is the minimum value, we are slightly increasing the value. You can take it 220, you can take it 225, 210. That is a good practice. So calculate D2. N1 and N2 are 40, 40 and 400. Assuming 100% efficiency, give me the value of D2. If you want, you can use 98% efficiency as well. For time being, let's go with 100% efficiency. So what is the next value? On V belt, we are very safely, we can ignore slip for V belt. Give me D2 for B and C. Answers please quickly. What is D2 for B section? It's 504 or 490. For 140 mm. Somebody please confirm. 504. For C, for C cross section. Till then, center distance. Maximum is 2 times D1 plus D2. Minimum is half of D1 plus D2 plus thickness. So we'll be taking this range D1 plus D2. Yeah, for C section. Vedant, Manas. Shashwat. 644 is the center distance. Richa, what is D2 for C section?
792 mm.
Sorry, what is D2?
And D2 is 792.
D2 is 792. And the center distance? One zero one two. Others, please confirm. Okay. Next, we have to get the value of theta. With the center distance known, value of theta is pi minus d2 minus d1 by c. Give me the value of theta. B and C section quickly. .57 for B, radians. C will get almost the same, 2.57. Okay, now we'll start with the correction factors. We'll start first with the equivalent diameter factor. This value that we have selected is a tentative value. Actual value you will get from this table. Equivalent smaller diameter correction factor DE. For both B and C, give me what is the ratio of D by D, that is D2 by D1, and accordingly refer the design data book. Give me what is DE, D2 by D1 for C, and give me what is the factor that is given on page number 7.62. Your value of D by D would be normally greater than 2.9. Is it 3.6? Is that D2 by D1 for both of you? Okay, that is same because it is equal to N1 by N2. So for 3.6, which is 2.9 and over this, the correction factor is how much? It is 1.14. So this 1.14 is multiplied to your small diameter. DE is D1 multiplied by 1.14. So what we have done is we have increased the diameter of the smaller pulley. This is a virtual value. So what is DE here and what is DE here? For B and C. Come on, B and C sections quickly. $159.6. You can go with 160 for B. For C, C is 250, 251. Okay. Next page, turn the pages. You will get rating for B built in kilowatt for cross section B and for cross section C. So those referring for B, your equivalent pitch diameter is around 160 now. And what is the belt speed? We haven't calculated belt speed in meter per second. You know the diameter D1, you know what is the peripheral velocity. Pi D1 N1 by 16. Find out what is VP here. What is VP here? And for this given value of equivalent pitch diameter, 160 for B section and 250 for C section, and we have to find out what is the belt speed. Whatever value you get in this table, that is the actual value of power rating. Peripheral velocity is coming out to be 10.56. 10.56 is for B. Please confirm others. .5 and 16.5. 16.5. Now refer this data book. For B, cross section B, refer equivalent pitch diameter 160 and your belt speed is 10.5. So you have 10 and 11. What you can do is take the average of whatever is the power rating for 10, that is 3.09, power rating for 11, which is 3.31. That is the actual rated power after this correction. This is page number 7.64. I don't know the page numbers if they are same. And for C cross section, the page number is 7.65. Your diameter is 251. Now you have the standard equivalent pitch diameters 240 and 260. Your value will lie somewhere in this range and your peripheral velocity is 16.5. So you will have to take an average of 7.87, 8.61, 240, 260. Similarly, 16 and 17 ka average. Or if you want to just simplify your value, if it is 251, you can pick up 260 equivalent diameter and take peripheral velocity as 17. Rather than getting the correct answer, understanding the procedure is more important. So what you are
Can you
getting for
repeat
B?
once again?
Yes?
Can you repeat?
Yes, I'll do. For B, cross section B, for the peripheral velocity 10.5, we have the value for 10 meter per second and for 11 meter per second. And your diameter is 160. So for 160 at 10 meter, the power is 3.09. For bell speed 11 meter per second and equivalent pitch diameter 160, the rated power is 3.31. So what you have taken for 10.5 is average of 3.09 and 3.31, right? And you got this value as 3.2. Is that clear for B cross section?
Yes, ma'am.
Similarly, for C cross section, now the value is coming out to be 250, whereas we have 240 and 260. So your value will lie in this range, 240 to 260. And your peripheral velocity is coming out to be 16.5. And we have the values for 16 and 17. So what you can do is take an average of 240 and 260 for 16 meter per second speed and an average for 240 and 260 for 17 meter per second, and again take another average. So your value will lie between 7.8 and 8.9. You can as well go with इसको 260 कर दो, इसको 17 कर दो, and this value will become 8.9. So that much approximation is acceptable. Here we are simply trying to understand the design procedure. Our aim is not to get an exact answer, but to understand the procedure. If you want to get exact value, you'll have to take an average from the data given. Is this part clear? For C cross section? Anshuman, you have given me the answer, which means it is clear to you. Okay, which means one belt with B cross section with this equivalent diameter can transmit 3.2 kilowatt of power, and if we are taking a C cross section, this can transmit 8.36 kilowatt of power. But this would again reduce with more correction factors. Next is angle of contact correction factor. What is the angle of contact in degrees? 2.57. What is equivalent in degree? For both, it is the same value. This coming out to be 147. Turn the pages, come to page number 7.68. Unless you solve it on your own, you will never understand what we are doing. Others, if you are simply copying from the screen, you would never ever understand what we are doing. So you see for VV belt and for 180 degrees, the correction factor is 1. As the angle theta decreases, the correction factor value decreases, and this will be multiplied to this rated power. And so the actual power transmission capacity will also go down. 148 का 0.92 है, 145 का 0.91 है. So we can safely go with 148, which is 0.92. So for both the cross sections, we are using K theta as 0.92. Which will be multiplied to this value of PL. Now the actual power transmission capacity again reduces by this amount. This we can multiply later also, we'll keep it here. When you multiply it with 0.92. The 2.9 is 3.2 multiplied by 0.92. For C section, okay, so this has reduced to 7.69 kilowatt. Next is length of the belt correction factor. Simpler one is service factor. पहले ये ले लेते हैं. Everything has to be multiplied and divided, and so the sequence doesn't matter. Correction factor देखो. A motor which is driving a reciprocating compressor working for 12 hours per day. Type of driving unit is motor. Running over 1440 RPM, and the driven unit is reciprocating compressor, which will lie in the heavy duty. Piston compressor is same as reciprocating compressor. What is the value of service condition? Motor running over 600 RPM. Apna RPM is 1440. How did you get 1.3? Working for 12 hours per day. Reciprocating compressor, this is lying in medium duty or heavy duty? Did you get 1.3? Are you the type of driven machine? Have you taken this as medium duty? Piston compressor दिख रहा है ना? Piston is used in reciprocating system. So it is a piston compressor, which is a reciprocating compressor lying in the heavy duty. So type of driven machine is heavy duty. Type of driving unit is a motor running at more than 600 RPM. So it is the second column for 12 hours per day. So what is the value? Heavy duty AC motor, 12 hours per day. It is 1.5. How are you getting 1.3 per day? It's rotating more than 600 RPM. Motor का RPM 1440 दिया है. You have to pick up the second column. First column is for motors running below 600 RPM. So we are going with 1.5. We are going to divide this or multiply this. With the service condition, the rated power will reduce. So we are going to divide this. So again, the value of actual PR.
Ma'am, how is it 1.5? Actually, the left side column is saying over 600 RPM.
So अपना over 600 RPM है ना, motor is running at 1440.
So it's showing 1.3 actually.
Yes, ma'am. For the right side column, it is under 600 RPM. And for that, it is 1.5.
Yes, you are right. You are right. First column is going showing over 600 RPM and second one is showing under 600 RPM. You are right. लेकिन ये गलत हो गया ना. At higher RPMs, the condition would be more severe. कि lower RPM में condition would be more severe. What do you say? What does the logic says? Conditions are more severe at higher RPM, and so this service factor should be higher for higher RPM. The higher RPM में lower value and lower में higher value of service factor is not correct, right? You agree? And if you agree, then we are dividing this. And we have one more we have one more correction factor, length of the belt correction factor. Find what is the length of the belt. You have the formula for length of the belt given in the design data book in terms of diameters and center distance. Length of the belt would be different for both sections. UC plus pi d1 plus d2 by 2 plus d2 minus d1 whole square by 4c. What is the length of the belt here? What is the length of the belt here? Two, 3, 5, 1 for B. Others please confirm. Vandana is giving 2, 3, 5, 1 for B cross section. Saurabh, what is the length for C? Two, 3, 5, 1 for B. And for the design data book, for the cross section B, and for this nominal pitch length, what are the values close to this? Standard values close to this. Check nominal pitch length cross section B. 2351 is your answer. The adjacent values given here are 2329 and 2507 for B. Roll number 60 and above, nobody is solving for what? Give me the answers. Only Saurabh is coming. Shriya, Prajwal, Manas, where are you? Okay, 3693. लेंथ ज्यादा है तो ज्यादा टाइम लगता है क्या? 3694. Okay. Refer the design data book for the nominal pitch length. What are the lengths available? Page number 7.60 for C section, 7.59 for B cross section. Second and third page where we have started the V belt. First page 7.58 is giving you the data for standard V belt section. Second one is giving you for the length. For C cross section, what are the nominal pitch lengths close to 3694? Three, 6, 5, 8. कहाँ दिख रहा आपको? Close to 3694 for C cross section. Where did you get the value 3658? I cannot see this. For B section, this is 2501 on the lower side and 2329 on the higher side. So a value closer to this on the lower and higher side are 2507, which is pretty higher, and on the lower side it is 2329. This value is closer. For 3694, cross section 3. What are the values you are getting? 3713 and 3694 से lower value लोगे ना विनीत? Isn't that 3459? You are not going to check nominal inside length. You have to check nominal pitch length. What we have calculated is we have to choose a closer length, not smaller or higher. Whatever you choose, you will have a you will have a correction factor. So for 3694, C section, nominal pitch length, you are not to see the nominal inside length. We have to see the nominal pitch length, third or second, third, fourth column. Yes. So it is 3459 on the lower side. Nominal pitch length. What we get by the calculation is a nominal pitch length, not the inside length. Which one is closer? 34 or 37? This one is closer. So what is the correction factor corresponding to 3713 for C cross section? Sania? For 3713, what is the correction factor for C cross section? Sushmita? 1. 1 for C cross section. Yes, and for B cross section for 2329. For B cross section, fortunately this KL is again 1. For 2329, KL is 1. And while you are still seeing, now you can see what is the nominal, what is the inside length, because this is required for what? For our designation. Once you have decided what is your pitch length, now you know what is the inner length. So corresponding to 2329, what is the inner length? 2286. So your belt is B2286. And for C cross section, what is the inside length? Corresponding to 3713. Inside length is 3658. This will need a lot of practice. Abhi, because you have changed the length, your center distance is going to change. Center distance we have assumed to be D1 plus D2. So ideally, after you get this length, pitch length as 2329, you should substitute this as length, D1, D2 remains the same, and calculate what is the corrected value of C. Belt length come ho gaya na? So this belt will become too tight, and so the center distance has to be corrected. And here we have taken a higher value of C. So if the value of this is taken as longer, there would be a more slack would increase, and so here also C should be corrected. So you have to calculate this, but before that, this part you can do. What is our final power transmission? The value which we have selected from the table for equivalent diameter multiplied by 3.2 for B section, which is multiplied by K theta, which was divided by service condition and multiplied by KL. So this is the value of PR multiplied by K theta multiplied by KL divided by the service condition KS. What is this value you got? Is that 1.96? And here, what is the value of power? This is transmitting 5.132. So you see this, a single V belt of C cross section is transmitting 5.132 kilowatt of power. Now we are finding out what are the number of belts required. So how many belts would require to transmit 15 kilowatt of power if each belt is transmitting 1.96 kilowatt power? And for C cross section, total power to be transmitted is 15 kilowatt and each belt is transmitting 5.12 or 5.13. How many belts are required? 4 for C cross section. And 8 for B cross section. Correct. Now you see which one is better. Number of belts 4 and number of belts 8. The size of the pulley, the width of the pulley, the cost, everything would increase with such a higher number of belts. And that's the reason if B cross section belt has a limit 2 to 15, 15 is the extreme. We should not pick up this. Picking up C is better because the range for C is 7.5 to 75. So 15 is always a middle range. So we'll try to avoid the extreme cases, minimum and maximum. And so this shows how C cross section is better. So the final selection of belt should be specified as C, kitna inner length, kitna inside length, 3658, C 3658, 4 number of belts. We'll solve one more problem on belt drive in the next class, and wherein we'll be using Shivalkar design data book, and then we'll talk about this pulley design also. What's your query? It can be 3. Number of belts. Yeah, what is this value coming out to be exactly? This would be 2 point something, 2.9. तब तो 3 भी ले सकते हो. Why 4? Go with 3. It's coming out to be 2.9, right? Okay, let me quickly explain you the entire procedure once again. Then we'll stop. You people don't remind me to start the recording. I'm recording now. Well, so we know that this is the formula for power transmission capacity of a V belt drive. which is calculated using this formula by performing a lot of experimentation where the lab conditions were theta is 180 degrees, velocity ratio is 1, specific length of belt is considered and there were no shocks. And the calculated values are given in the table. So we have referred to the table, and since the real life conditions are different from lab conditions, so we have to have some angle of contact correction factor. If the value of theta is less than 180 degrees, we will multiply some correction factor which will reduce the power transmission capacity of the belt. Similarly, lab condition says that the diameters are same, but in the real life condition, the diameters are not same and the bending is more severe and less severe in the pulleys. So it is virtually, we are increasing the diameter of the smaller pulley and reducing the diameter of the larger pulley. And this increase in the smaller diameter pulley, this depends upon the ratio of the pulley diameters. From this ratio, we get a factor which we multiply with the smaller pulley diameter to get the equivalent pulley diameter. And from the table given, depending upon which cross-section of belt we have selected, for this equivalent pulley diameter and for the peripheral velocity calculated based on D1, we find out what is the rated power. This is taking into account the variation in the diameter. Next correction factor is length of the belt correction factor. So we calculate some pitch length using the formula. Now this pitch length will not be equal to the pitch length exactly which is tested in the lab, and so the center distance would vary. So we have to go with either a larger length or a smaller length of the pitch length. Accordingly, there would be a correction factor which needs to be multiplied. This correction factor will again change the value of actual power transmitted. And then the working condition, depending upon heavy duty or light duty, we have what is the actual power transmission. So this is PR based on the equivalent diameter. K theta depends upon angle of contact, KL depends upon the length correction factor, and KS depends upon the service condition. If your design data book is giving service condition greater than 1, we divide. Suppose the problem statement is giving the service condition is 0.8. In that case, it is less than 1, we multiply it. So this will give you the power transmission capacity of single belt. We divide the total power transmission capacity by this term to get number of belts. Now the same thing, we are trying to solve a problem where we have to transmit 15 kilowatt power between 1440 RPM motor to 400 RPM compressor working 12 hours per day. As per the design data book, 15 kilowatt power can be transmitted using B and C, both the cross sections. We should normally pick up a value of power which is lying between the extreme ranges. So ideally we should pick up C, but let's see what happens if we pick up B. Minimum pulley diameter is given. We should take little higher than this value. By 10 or 20 mm higher you can take up. With D1 and D2 known, find the center distance. Minimum center distance is sum of their radii plus thickness. Maximum is 2 times the sum of their diameters. We are taking an intermediate value D1 plus D2. From the center distance and diameters, we calculate what is the angle of contact, which comes out to be less than 180 degrees. From the ratio of diameters, we find out what is the diameter correction factor, and we have increased the smaller diameter from 120 to 160, and here from 225 to 251. And for this equivalent small diameter and for the peripheral velocity, we got the rated power from the table as 3.2 kilowatt for B and 8.3 kilowatt for C cross section. Then angle of contact K theta, we convert this theta in degrees and we see that for 180 degrees K theta is 1, for 147 degrees K theta is 0.92. So this power transmission capacity further reduces by 8%, and this comes out to be 2.94 and 7.69 for B and C cross section. Next is the service condition. Depending upon the RPM, depending upon the driving and the driven machinery, we got the service condition as 1.5, which will further reduce its power transmission capacity. And next is the length of the belt correction factor. So we find out what is the length using this formula. This is giving us a nominal pitch length. You calculate this value from the design data books, check which one is a lower and a higher value. Whichever value is closer to your calculated value, that will select, and on the same table in the same line, you will find out what is the correction factor. So fortunately for both B and C, for the calculated length, we got the correction factor as L1. And this is a nominal inside length. The inside length is the minimum length on the belt taken on the inner corner or on the inner side. So this is 2286 and this is 3658. Here we have to do one more step because length of the belt is changed. Center should also be corrected, center distance. So this calculation you have to do by substituting this value as in L. D1, D2 remains the same. Get the value of new center distance C. And then the actual power is the power from the equivalent smaller pulley diameter multiplied by K theta multiplied by KL upon KS. So for B cross section, each belt is transmitting 1.96 kilowatt power, and for C cross section it is transmitting 5.13 kilowatt power. And so we find out the number of belts required to transmit total 15 kilowatt power, which comes out to be 8 here and 3 here. The more the number of belts, wider would be the pulley, heavier would be the pulley, and so it's better to select C cross section. So selection of belt says it is C type cross section with this as the inside length, 3 number of belts, and you have to also specify the corrected center distance with center distance equal to. This completes the design of V belt, and then we are left with the pulley design, which we'll discuss next class. Well, now you are free to ask your queries. Shubham, why not to choose belt section such that only one belt is enough? You don't have such a heavy section which will make a single belt enough. 15 kilowatt ke liye you have either B or C. You cannot go with D. D is recommended for 22 to 150. You cannot have a very heavy cross section. We don't have to check for strength because all those tests, they are already done in the lab conditions. So we have to simply, we are not designing a V-belt, I told you. We are selecting a V-belt from the design data book. Okay, we have a different approach for designing a V-belt from Shivalkar data book. This that we'll discuss in the next class. No, D doesn't work. With correction factor, yes, it will come down to 15 kilowatt, but the standard procedure says that depending upon the final power to be transmitted, you have to pick up from this table. So this is as per the standard manuals which come with the belt drive. For D cross section, you see the recommended minimum pulley diameter is very large, belt size is very heavy. Why did we take center distance as D1 plus D2? Minimum center distance is sum of their radius plus thickness. Maximum center distance is 2 times of D1 plus D2. So we are assuming a center distance in between a range of minimum to maximum. So for all the problems, you can safely go with D1 plus D2. Length nikalne ke baad you can correct it. So this will slightly get modified. Taking on a maximum side will make the entire setup very bulky, huge space. Taking on a minimum side, there is a little variation, though center distance bahut kam ho jati hai. So we'll always select a value which is like between the range of minimum to maximum. Any more questions? These were really good questions. Your questions also tell me how much the concept was clear to you. Utkarsh, Abhijit, do you have any questions? Vinayak, Sahil?
Ma'am,
Yes?
why does bending load decrease with increase in center distance?
It will bend less frequently, right? If the center distance is large, यहाँ से वहां तक belt जब जा रहा है from this end to other end, It is getting sufficient distance to relax, and again it has to bend. Again, it has getting a lot of distance and time to relax, but with this lesser center distance, it bends more frequently. For the same RPM of the belt, it has to bend many times. Can you visualize this knee belt rotating between the two pulleys, bending more frequently?
Yes, ma'am, got it.
Okay, good. What else? Okay, so if there are no more questions, should we stop? Vineet, Sahil, Ujjwal? Okay, no questions. Thank you all. We'll stop here. See you again on Tuesday.